Bismillah, this is Dr. Magda Talib Al-Hinai from the Department of Mathematics and Statistics, Sultan Qaboos University, presenting transformations of functions. This presentation is exclusive for the Independent Learning Center. We start our presentation of transformations of functions with vertical shifts. Here we explain how we can shift a function upwards or downwards. Suppose we have a function f of x, the graph of which is given in red in front of us, and we have a positive number a. If we add a to the f of x, we get a new curve which is exactly like f of x in trend but different in magnitude by an amount a. So adding a to each value of f of x, we get f of x plus a, which is in front of us in green color. This f of x plus a is a vertical shift upwards of the function f of x by a units. Now we go to the other case when we subtract a from f of x. The graph of y equals f of x minus a, where, as I said, a is a positive real number, is the vertical shift of the original function in red f of x downwards by a units, as we see figure to the right hand side. Okay, so if we have a look at both graphs and we see the f of x in red in both figures, to the left hand side I get f of x plus a by vertically shifting f of x a units upwards, while in the figure to the right hand side we get f of x minus a, which is in blue color, by vertically shifting f of x downwards a units. Let's explain vertical shifts by an example. Suppose we have the function f of x is equal to absolute value of x. How can we use the graph of f of x to graph or to sketch g of x equals absolute value of x plus 2? Here we have f of x equals absolute value of x, and the graph of this function is the standard absolute value function, which is shown in front of us in black color, while the graph of g of x equals absolute value of x plus 2 is given in red color, and we obtain it by adding 2 to each value of absolute value of x. So we shift the graph of f vertically upwards 2 units to get absolute value of x plus 2. Here is another example. Use the graph of f of x equals x squared to obtain the graph of g of x equals x squared minus 2. So we do this in 2 steps. Step 1, we graph f of x equals x squared, and we all know that x squared will, when we graph it, we get the standard U shape, which is a parabola open upwards having its vertex at the origin. Now, in order to graph g of x equals x squared minus 2, we add minus 2 to each value of x squared, and we do the shifting vertically downwards 2 units of the parabola x squared. As we see in front of us in the figure, x squared is given in blue color, while x squared minus 2 is represented in red color. Now we move to horizontal shifts. So let f be a function and a positive real number. And we have the graph of f of x in front of us. I put it in red color. The graph of the new function y equals f of x plus a, as we see, the a is added to the variable x. Okay, so the graph of f of x plus a is the same as the graph of f of x, but shifted a units to the left. This is a horizontal shift to the left hand side. Now, what about the graph of f of x minus a? And as I said, a is a positive real number. We see it in front of us in the figure below. Here is f of x. We have it in red color. And f of x minus a, we give it the orange color, and it is a horizontal shift of the f of x towards the right by a units. Here comes an example with the two kinds of shifts. The example says, use the graph of f of x to obtain the graph of h of x equals x plus 1 all squared minus 3. Here we meant that f of x is equal to x squared. This is the standard quadratic function, and we will give it the red color. So if we go to the figure, we see that f of x equals x squared is drawn in red color, and it is a parabola open upwards with its vertex at the origin. Now we graph g of x, which is x plus 1 all squared. So I'll take only the x plus 1 all squared and I will try to graph it. So since 1 is added to each value of x in the domain, we will shift the parabola x squared in which direction? Yes, horizontally to the left by 1 unit. Now what's next? We have x plus 1 all squared minus 3. As we see, 3 is positive and we subtract it from x plus 1 all squared. So this tells us that the blue curve representing x plus 1 all squared, after subtracting 3 from it, will be giving us the green curve, which is x plus 1 all squared minus 3. The green curve is a vertical shift of the blue curve 3 units downwards. Now we move to reflections. We start by reflection about the x-axis. The graph of y equals minus f of x is simply the graph of f of x but reflected in the x-axis. So if we give f of x the blue color, minus f of x, we'll give it the pink color. So we see the mirror reflection in the x-axis of f of x and minus f of x. Next, we see the reflection about the y-axis. The graph of y equals f of minus x is the graph of f of x reflected about the y-axis. Again, I will put f of x in blue color and its mirror reflection about the y-axis, f of minus x, I'll give it the pink color. And if we have a look in front of us at the graph, we see the mirror reflection I'm talking about of f of x and f of minus x. Next, we discuss stretching and shrinking of graphs. We will only discuss the vertical stretching and shrinking in this video. Suppose we have a function f and a positive real number a. If a is greater than 1, then y equals af of x is the graph of f of x vertically stretched by multiplying each of the y coordinates by an amount a. So if we look at the curves in front of us, we see x squared, for example. This is given in green. And then we try to graph 2x squared. So we will find that the 2x squared is simply the vertical stretch of x squared. And we can see this in front of us very clear if we have a look at 2x squared, which is in blue, and x squared, which is in green. Now, what about the shrinking? Suppose we take a to be some real number, which is positive, but at the same time less than 1. The graph of af of x will be the vertical shrinking of f of x. And this will be clear if we have a look at the graph in front of us, looking at x squared and half x squared. So we multiply each of the y coordinates by half. So this makes the curve x squared shrink vertically by a factor half. Here we give you a very important hint of the sequence of transformations. We perform transformations by following the order in front of us. We first do horizontal shifting and then vertical stretching or shrinking. And then we do the reflecting. Finally, we do vertical shifting. Let's take an example on this. This will be our last example for this video. The example says, describe how the graph of y equals minus 3 multiplied by x minus 4 all squared plus 5 can be obtained by transforming the graph of x squared. Then sketch the graph. So we need first to explain how we do the transformations, and then finally we need to sketch the graph of y equals minus 3 multiplied by x minus 4 all squared plus 5. Okay, the basic graph we are using is x squared. We draw it first. Then after drawing x squared, we see we have x minus 4 all squared. The minus 4 here tells us that we are doing horizontal shift because it is x minus 4 all squared. So we are doing a horizontal shift by 4 units to the right hand side. Yes. Now the coefficient of x minus 4 all squared is a minus 3. I'll take it step by step. I'll take the 3 first, and then I'll take the minus sign. So multiplying x minus 4 all squared by 3, this tells us that we are stretching vertically by a factor of 3. So when we graph 3 into x minus 4 all squared, this will give us the green curve in front of us, which is a vertical stretch of x minus 4 all squared by a factor of 3. Now we apply the minus sign. The minus sign, when applied to 3 into x minus 4 all squared, this will give us a reflection in the x-axis. Finally, we add 5. Okay, adding 5 to minus 3 into x minus 4 all squared means that we will shift this graph, which is in red in front of us, vertically upwards by 5 units. Finally, we get minus 3 into x minus 4 all squared plus 5 in front of us in the purple color.